This is lesson 4 of chapter 5, and in this lesson we'll continue talking about periodic table trends. The next trend we'll discuss is something called ionization energy. Now this is a strange trend, not strange but unfamiliar really. So the word ionization, you can hear the word ion in it. This means you're making the element into an ion. And the way you're making it into an ion is by removing its electron. So this is defined as the energy required to remove an electron from an atom or an ion. And the units for this is kilojoules per mole, because energy, remember, is given in joules, the unit joules. Here it's going to be a lot of joules because we have a mole, we have a huge amount of these atoms, so it'll be kilojoules, just like kilograms is a lot compared to grams. So the way that we designate this is IE1, meaning ionization energy 1, is the energy to remove the first electron. IE2 is the energy to remove a second electron. IE3 would be a third, and so forth. So what we're doing essentially, here's the atom, and we're removing the outside electron from the atom, just the outside electrons, one by one. And then we're measuring how much energy it takes to do this. So if you take a look at the trend, what you'll see is the trend shows a nice pattern on the periodic table, with the smallest ionization energy being at the bottom left and the biggest ionization energy being at the top right. Now if you recall, when we talked about atomic size, this was the opposite. So we saw the helium was the smallest atom and then cesium was the biggest atom. And the reason this correlates is because the smaller the atom, the tougher it is to remove the electron because it's closer to the nucleus. The bigger the atom, the easier it is to remove an electron because it's furthest from the nucleus. It'd be like if a person was holding, say, you had to remove a basketball from their hands. If they were holding it out far, it's easier to remove it than if they were holding it very close to them. The same thing with electrons. So that's why you see this trend on the periodic table. Now, this is a general trend. You'll see that in general, as you go down a group, notice how ionization energy decreases, right? You go from 520, 496, 419, because the atoms, remember, are getting bigger and bigger and bigger as you go down a group. As you go across a period, going this way, the ionization energy increases. So 520, 899, 10, 14, 16, 20. So that's because the elements are getting smaller and smaller and smaller and smaller, and it takes more and more energy to remove them. Now, there are anomalies, there are breaks in the patterns. Notably, there's a break here, there's also a break here, and these breaks are actually between the subshells. So remember, this is the S subshell, this is the P subshell. Notice there's a break between here. It does not follow the pattern. And this is actually one of the confirmations of our idea of subshells. So this is experimental data that confirms that our idea of subshells is correct. So this is a quick overview of it. Here are the reasoning for why. Here it says ionization energy is generally decreased down a group and increase across a period. And again, this is linked to the size of the atom. The smaller the atom, the tighter it holds electrons and the more energy it takes to remove the electrons, which is what we just discussed. So this also explains the trend of reactivity. If you ever take a look at the reactivity, say, of the first group, this is lithium, sodium, potassium, these are the alkali metals, you'll see that they become more and more reactive. Usually lithium, if thrown into water, creates a little bit of reaction. Sodium a little more, potassium more, rubidium quite a bit more, and on and on. And so these elements, you can see a trend of reactivity. So reactivity increases as you go down. And that's because it becomes easier and easier to remove an electron the further it is. And because reactivity depends on electron movement, electrons are being removed much more easily, so the reactivity increases. Now, if we take a look at ionization energies for the same element, the first, the second, and the third ionization energy, here we see that the first ionization energy is smaller, the third ionization energy is the biggest. Notice this is the less than sign. So why is this trend true? Well, every time you remove an electron, the atom gets smaller because the nucleus draws the remaining electrons closer to itself, and then the atom becomes smaller. If you decide to remove a second electron, then the nucleus will get we'll keep pulling the electrons in, the atom will get even smaller, and on it goes. So every time you remove an electron, the atom becomes smaller, so now it takes even more energy to remove the electron, and that's the reason for it. So we can talk about the differences in ionic size to help predict this. So we have a few questions here. The first question is, which is bigger, chlorine or chlorine minus 1? Now remember, this is the chlorine atom because it is neutral. This is the chlorine ion because it is negative. Actually an anion, to be more specific. Now because anytime you gain electrons, electrons add to the outside of the atom, chlorine will actually be smaller and this chlorine ion will actually be bigger. The difference won't be that huge, but it'll be something on the order of, it'll be very noticeable. So if you have this chlorine atom is this big, this chlorine ion will probably be roughly that big. So the size increases if you add electrons. If you take a look at cations, these are positive ions. Copper has a +1 charge, this copper has a +2 charge. So think to yourself, which one has more electrons? Well, because this has a higher charge, it lost more electrons. So if it lost more, it has less electrons. This copper atom, say, or ion, will look like this. This one, because it's lost more, will look smaller. So the bigger one then is this one. And in this case, the bigger one is this one. These are the two answers. So hopefully this makes sense in terms of electrons. Go and try this on your own, this practice problem. And then let's make some general statements about ionic radius. Here we say that cations are smaller than atoms and anions are bigger than atoms of the same element. What we're saying is if you become a negative ion, you actually become bigger. If you become a positive ion, you become smaller. And that's kind of the idea. So hopefully this concept makes sense. Next trend we'll talk about is electron affinity. And this is similar to ionization energy, which we just talked about, in which you remove electrons. Well, here, electron affinity is you add electrons. The word affinity actually means the desire for. So there are some atoms that love electrons more than others, and if you give an electron to an atom, it will release energy. The reason it releases energy is because, in a way, it thanks you for that electron that it really wanted. It's just kind of like if, say, if you need a few bucks to go grab yourself a McChicken or something, a friend will give you $1 and you will thank them for it. Similar with elements, they release energy by thanking us for giving them electrons. And this is given, again, in kilojoules per mole because joules is the unit of energy. Now the trend for electron affinity for the elements is actually like this. Electron affinity increases as you go up, and it increases as you go across. So the element with the highest electron affinity will be found in the upper right-hand corner of the periodic table. In fact, that is fluorine. Fluorine has the highest number if you analyze them. Actually, chlorine and fluorine are, chlorine is a little higher, but chlorine and fluorine will say have the highest electron affinities. Fluorine has the highest of the next trend, as we'll see the final trend. And then the lowest ones are down here. So you can think of this as the upper right-hand corner of the periodic table has the highest desire for electrons. The lower left has the least desire for electrons. Now we know that metals like to give up electrons. That's why metals have a low electron affinity. Non-metals like to gain electrons. Fluorine, for example, wants to become a fluorine -1 to be like neon. It's so close to gaining an electron to be like neon. Sodium, on the other hand, wants to lose an electron to become like neon. So sodium does not want an electron, it wants to give one away. And this is why the reasoning for this trend. And this also explains the reactivity of the halogens. If you take a look at these 4 elements, fluorine is the most reactive element, the most dangerous element, one of the most dangerous elements of all, actually, is fluorine. And because they desire electrons more and more as you go up a group, this is why they become more and more reactive as you go up a group. And then the last trend that we'll talk about is something called electronegativity. This is actually similar to what we just talked about, electron affinity. But electronegativity is how strongly an atom in a compound attracts electrons. So when these elements become compounds, when they react with one another, they exhibit this trend. So this trend applies to compounds, not to pure elements. So here's what it means. Say if carbon and hydrogen were to form a bond, this is the a representation of a bond between these two atoms. The electrons that they're going to bond through, other outside electrons, they will be sharing those electrons. Now, the sharing in carbon and hydrogen here is actually equal, but compared to oxygen and hydrogen, the sharing is unequal. Oxygen has actually grabbed more of the electrons toward itself. It's pulling electrons more toward itself. And this is just a fact about elements. Some elements want electrons more. So when oxygen is forced to bond with hydrogen, it pulls the bonding electrons toward itself. Carbon does so a little bit, but not as much. And the trend for electronegativity, by the way, you can think of electronegativity as the negativity, meaning electrons have gained, or atoms have gained electrons, so they become negative. So this is also a measure of how much elements want electrons. But the idea here is the trend is the same as electron affinity that we just saw. The most electronegative elements are in the upper right of the periodic table. The least electronegative elements are on the lower left of the periodic table. So just like electron affinity trends, the two are actually talking about the same thing, except this one talks about in terms of compounds. The elements have to be in compounds. So why don't we try a little example? Before we try an example, we should mention that the four most electronegative elements are these. Fluorine is the most electronegative. Then oxygen is after him, nitrogen after him, and finally chlorine. These three are very special in their electronegativities. So they will have absolutely the greatest, and whenever we talk about bonding, when these decide to bond, they will be electron hoggers. They will hog the electrons for themselves. Incidentally, there are no values for the noble gases for electronegativities because they do not form bonds. That's actually a good fact to know. No, they do not form bonds. You can say they don't form bonds. Okay, so why not we take a look at an example problem, and we'll finish it with this. The question is, in carbon monoxide, are electrons pulled more toward oxygen or more toward carbon? Well, for this, let's ask which is more electronegative, carbon or oxygen. If you take a look at the periodic table, here is carbon, and here is oxygen, carbon and oxygen. So because oxygen is more to the upper right, oxygen is more electronegative, so oxygen will grab the electrons more for itself when they decide to bond. And that's how you decide. Again, if carbon and oxygen are bonding, the electrons are going to be pulled more toward carbon. Or, I'm sorry, more toward oxygen. I misdrew that. Let's try again. As they're bonding, the electrons are pulled more toward oxygen, this way. The second question is, which bond will cause the biggest difference in electronegativity? This question is a bit different, but the difference between hydrogen fluorine, carbon fluorine, oxygen fluorine. Now, if you take a look, hydrogen sits right here on the periodic table. Fluorine, good old fluorine, is all the way on the right, being the most electronegative element. So because the difference is biggest between hydrogen and fluorine, it will win. So biggest difference here. And the difference is biggest because they are the furthest apart from each other. The closer the elements are, for example, oxygen and fluorine are the closest, the difference is going to be smallest between them, and so there's not going to be a big difference in electronegativity. They'll be sharing for the most part roughly equally. Fluorine gets some electrons, oxygen gets some electrons. But in this case, fluorine actually pulls the electrons toward itself overwhelmingly. So fluorine gets all the electrons, hydrogen gets nothing. In fact, you can even roughly erase hydrogen's electrons. Hydrogen does not get much. Okay, so go ahead and try this on your own. Try a practice problem with the same concept, and this will complete for us the fourth lesson and actually the whole chapter of the periodic table. And for this last picture, this is a picture of Mr. Mendeleev himself with the Russian word for the end.